So, when my friends and I, we learned the release date of Stranger Things Season 2, we started planning a viewing party at my friend's house. It was weeks in advance, and I remember the day that it actually dropped. I got off work and I grabbed pizzas on the way to their house, and I was the last one in the door, and we tossed the pizzas down on the ottoman, and we started streaming. And we weren't alone. At Netflix, we're delivering experiences like this one en masse across the globe. We measure our success by the delight that we bring to our customers, by connecting them with amazing content and amazing artists. And as engineers, building the back-end systems that power these experiences puts us in a critical position. Because at Netflix, a majority of our customers are consuming our content exclusively through the systems that we're building. This means that the decisions that we make as engineers, they have a direct impact on our members' perception of our brand. So when we decided that we were going to build a serverless-like experience at the edge of our infrastructure for our device engineers, a platform that was going to handle every request from every device of all 130 million plus members that we have, we knew the decisions that we were making and the choices we took along the way would have a lasting impact on how the world viewed Netflix. My name is William Blankenship, and today we're going to be talking about how we're innovating with confidence. We're going to start off by introducing the constraints and the challenges we are facing as a company that led to us building this platform. Then we'll introduce the platform itself, and this should give us all a shared point of reference when we start talking about the tools and technologies that we're using to de-risk change. From there, we'll dive directly into the decisions we're making and the choices we're making to de-risk the changes that get introduced to our system through the platform that we're building. While this talk is about us building and migrating to a serverless-like experience in Netflix, it's really generalizable to de-risking any change that you're undertaking in your organization. So you should be able to take this presentation home with you and use it as inspiration for de-risking the changes being introduced to the products that you're building. And then we'll finish the talk by going over where we're at with our migration. What have these patterns unlocked for us? So let's start by introducing the challenge that we're trying to address. So if you take a moment and you think about all the devices that you have that have a native Netflix application. At Netflix, one of our value propositions is that we're striving to provide an experience that delights all of our customers across a massive range of consumer devices. We've accomplished this by bringing together a group of amazing device engineers who specialize in bringing the Netflix experience to each of these devices. The experience on each of these devices is populated by the back-end systems at Netflix. And each of these devices have a unique set of APIs and resource constraints that has required or driven the need for our engineers to have fine-grained control over that client-server interaction. And this has driven the need for our device engineers to be able to, deploy server-side business logic. The challenge is that we've hired these world-class engineers who specialize in building applications for these consumer devices, and these teams that we've built around these devices, they're not staffed for handling the problems that come with building and maintaining distributed systems. So what we're trying to find is a way for device engineers to build and deploy server-side business logic without all of the engineering challenges that come with maintaining and operating these distributed systems. So for my team, these are our customers. Our customers are Netflix device engineers bringing the Netflix experience to the devices in your homes. These device engineers are wanting to build and operate that server-side business logic to power the Netflix experience on those devices. And these teams, they're not staffed for maintaining these distributed systems. This means we need a clear division of responsibility between these device engineers and the SREs and infrastructure engineers building the infrastructure underneath this business logic. What we want to provide is a serverless-like experience for these engineers. We're building a platform that abstracts all of the complexities of developing and deploying to Netflix's infrastructure away from these engineers. And without further ado, let's introduce that platform. So the platform itself hosts Node.js services. We handle HTTP routing inside of this process using an open source framework called Restify. And our users define which function handlers they want to have invoked on which HTTP methods and requests. And these request handlers, they're just standard Restify request handlers. You get access to your request object, your response object, and you can control Restify's middleware execution chain by invoking the next callback. On top of this, we provide pre-configured sets of tools and APIs for interacting with the Netflix ecosystem. So just by deploying to this platform, your service is automatically going to be deploying or publishing metrics around RPS, CPU utilization. It'll be publishing logs and tracing information for every request coming through the front door. So as engineers operating these systems once they're deployed, we have a standard set of metrics and a standard set of services so we can operate these in a standard way. And when it makes sense, we expose these pre-configured APIs to our developers so they can do things like logging and publishing metrics without having to worry about configuring those APIs and knowing where they're publishing this, that information to. And as an engineer, if you wanted to get started developing for this platform, we have a tool called Newt, which makes it incredibly easy. You would run Newt init, and Newt would set up all the project scaffolding for your service. So it would set up everything you need for developing a Hello World application. But this isn't just about local development. Newt init will also go through and set up all of the CI/CD deployment pipelines that are necessary to carry that service to production. And it'll automatically configure all the alerts and dashboards necessary for us to operate that service once it's deployed. So by the time you're done running Newt init, you'll have a Hello World application that can be safely deployed to production and can handle Netflix scale traffic. At this point, you can run Newt develop, and it'll take that service and it'll build it as a Docker image and it'll spin it up on your local machine. And while it's running locally, it's actually going to be connected to our company's VPN. So requests that go through our front door or gateway will get routed to that container running on your laptop. And that container can also talk to the rest of the backend services at Netflix. So this gives a developer running a local development experience, but still all of the benefits that you would get from deploying and iterating on infrastructure itself. You can also run Newt test. Newt test will do the same thing as Newt develop, but then it'll spin up all of your integration tests and your unit tests, and it'll run them directly against that image that you just built. And Newt publish will take that image and push it out to our Docker registry. At this point, you can run Newt deploy, and that image will show up in production. What are we deploying to? So Netflix has built and open sourced a container orchestration layer called Titus. Titus takes these containers and it deploys them directly to EC2 instances. When a customer's device makes a request to Netflix's API, the request will pass through Zool, our open source gateway, and Zool will route that traffic out to our containers running on Titus. From there, those containers will reach out to the rest of the microservices and data stores at Netflix, assemble a response, and send it back to your device. So while this system doesn't necessarily meet the exact definition of what most would call serverless, since we're deploying to EC2 instances, we're still owning and operating all of our servers, what it does unlock is a serverless experience for our developers. All of the complexities of owning and operating the infrastructure that's abstracted away from them. And this has allowed us to set up our organization for success by clearly delineating the responsibilities of building and deploying this business logic from all of the responsibilities that come with infrastructure engineering and SREs. So what this means is that we, as SREs and infrastructure engineers, we can make huge strides in de-risking the changes that get introduced to this business logic, all without significantly impacting our developer workflows. So our developers can continue doing what they're doing, and we can improve this, the reliability of the system. Which brings us to the core of this talk. What are we doing as engineers to reduce the risk that changes pose to our system? We're going to talk about three main approaches. We're going to talk about isolating change. We're going to talk about reducing the blast radius of those changes. And then finally, we're going to talk about minimizing the risk that unintended changes pose to our infrastructure. But first, I think a natural place for us to start is how we're approaching migrating to this new platform, since that approach actually encompasses all of the three other approaches that we're going to be talking about. So we've taken an approach known as the strangler pattern. This was coined by Martin Fowler, and it's named after the strangler vines. These vines, they sprout in the canopy of trees, and they grow down to the earth. And as they grow down to the earth, they consume more and more of the host tree until there's nothing left. So we started with an existing system, the legacy API at Netflix. And we started spinning up services that handled we started spinning up services that handled a small surface area of that original API. And we introduced a few twists. The first twist on this pattern we introduced was that these services initially, they didn't actually do anything. All they did was they proxied the requests directly back to the API. Then we started implementing a small portion of the responsibility that we'd be, or the API that we'd be responsible for moving forward in this service. Anything we couldn't handle, we would continue proxying back to the legacy API. And we introduced a second twist. We created a knob at our gateway that allowed us to tune the amount of traffic that this new service would receive. Everything else would be routed back to the legacy API to be handled. This allowed us to introduce this new service to a small percentage of production traffic. Little by little, we shifted more responsibility and more traffic to this API. Until finally, this new service, it was handling all of the responsibility and all of the requests, and the legacy API was receiving nothing. And we're doing the same thing for the rest of that API surface area. Little by little, we're migrating more and more responsibility and more requests to our new platform until one day, there'll be nothing left going to it, or to the legacy API. So what did this pattern, or strangler pattern, unlock for us? First, it allowed us to iterate with a tight feedback loop. So our engineers, or instead of stacking up all of our changes into one big, massive system and exposing them to the world all at once, we're able to chip off small parts of the legacy API and migrate it to our new platform in isolation. This allowed us to get quick feedback on the correctness of these services without all the risks that come with a full deployment. On top of that, this allowed us to reduce the blast radius. By exposing this new platform to only a very small percentage of traffic at first, any changes that broke production only impacted a small percentage of traffic. And most importantly, in the early days of our project, when we were still hardening the platform itself and all the infrastructure underneath, what this allowed us to do is, by striving for feature parity, we always had the option to fall back to the legacy API. So if our logger went sideways and started filling up disks and our tier fell over, we could turn that knob to send 100% of traffic back to the legacy API and restore the streaming experience for our members without having to ship a single line of code or fix any of the underlying infrastructure. Once we were delivering the experience to our members, we could then go in, fix our tier, validate the changes, and shift the traffic back. And finally, what serverless and microservice development really unlocked for this pattern was the ability to take a very small surface area of the original API and migrate it by itself. This allowed us to get a stable implementation of the surface area with feature parity, and then we could protect it from regressions that were introduced in other parts of the development cycle while we were migrating other parts of the API, since those migrations were happening in their own isolated process spaces, and they were happening in their own containers. Which brings us to our first big tool in de-risking change, which is the need to isolate changes that get introduced to our systems. So if we go back to our legacy API, or to our new platform, and we focus in on just a few of these services. Each of these services, they get their own code repositories. This allows us to track the changes that engineers are introducing to production at a very granular level. On top of this, in addition to having their own code repository, each service also benefits from having their own independent deployment pipelines. As opposed to a monolith, where oftentimes quite a few changes all get built up over time and then get deployed into production at the same time and show up in the same process space at the same time, this allows us to surgically introduce change into the system by itself. To maximize the value out of this, all of our deployments publish their metadata to an internal system called Kronos. Kronos allows our on-call engineers, when they detect a regression in production, to quickly answer the question, what's changed recently? Once deployed, each service is then benefiting from running in its own isolated Docker container and publishing its own isolated set of health metrics. Armed with this, we can quickly identify when a new change is breaking production. So what this is unlocking for us is a way for us to surgically introduce changes into our system. And then we can centrally track those changes so that when something happens, we can answer what's changed recently. And finally, the precision of the way we introduce these changes helps us deconflate the root cause when we're responding to an incident. If you can narrow down the scope of an incident to a single service, you can trace that service back to the code changes that were introduced. So as an on-call, or for example, so like if you're seeing headers being misparsed by one of your services and you look at Kronos and you track your deployment pipelines back to the code repository and you see an engineer has recently changed the way headers are being parsed, as an on-call, you can be pretty confident that that's the root cause of this problem, which lets you know whether or not falling back to a previous version of the service is going to restore the streaming experience, or if you're going to have to fix forward. So now that we have the means to detect when one of our new changes are breaking production, we want to marry this with a pattern that reduces the blast radius of this change. We want to reduce the potential for a new change to catastrophically break same is true for our builds and deployments. Things that we would like to depend on being 100% infallible and deterministic are in fact not. Things like writing files to disks and pulling bits over networks and running sed against a configuration file, these things work a vast majority of the time. And in fact, their error rates may be so low that as a developer on your local machine, you'll never encounter them. But when you're operating at a massive scale, things that are pretty uncommon to encounter on your local development machine become pretty common out in our infrastructure just because of the sheer frequency at which we're executing these code paths. To get the full benefit of the patterns we've just introduced, what we need are tools and practices that reduce the opportunity for unintended changes to seep into our deployments. We want strong guarantees that if I build and deploy a service, that the service that shows up in production has the same bits and the same configuration as what I was testing against. So what we want to do is minimize the unintended changes that get introduced to our system. Today, we're accomplishing this at our tier by tightly controlling our build process and by baking as many guarantees as possible into the artifacts that we're building. If we remember back to the introduction, we introduced a tool called Newt. Newt allows us to build our artifacts in a consistent way, both on your local development machine as well as out in CI and CD. And it does this by using Docker. Newt gives us a consistent way to generate artifacts through the entire development process. The artifact that comes out of Newt is just a Docker image. And these artifacts, the Docker images, they give us a lot of strong guarantees. To understand why, we need to look inside. These images, they're actually layered artifacts. And when we build these layers on these images, the layers are built within the context of the previous layers in the image. So our builds define a base image to start building from. And this base image, it provides things like the operating system, GCC compiler, the Node.js runtime, NPM, and much more. What this means is that when we build these layers, they're being built against the toolchain that we provided, not the build machine's toolchain. So it doesn't matter if you're building this on your local laptop or if you're building it out in CI/CD. Your build is being built against the same exact toolchain that we specified. This gives us a strong control over the deterministic nature of these builds and makes them more consistent. On top of that, these images, they're versioned and hashed. By hashing these, we get strong guarantees that if we download an artifact, that the artifact that we pulled over the wire is the same one that we asked for. So if we have an image that contains everything we need to run an application, and it has built-in integrity checking, what can we do with this? So for starters, we can take our unit and integration tests, and after every build, we can run them directly against the artifact that we built. This gives us strong guarantees that our build process is giving us valid and consistent builds. On top of that, not only can our customers run their builds or unit tests and integration tests against this artifact, when our team builds and deploys a new platform version, that platform can run not only its unit tests and integration tests, but all the unit and integration tests of our customers as well. So we can get strong guarantees that the images we're deploying are both correct and that the changes that we're introducing as platform engineers aren't breaking our customers. Now, when we go to deploy this artifact to production, instead of SSHing into a bunch of machines and executing a series of commands to try to bring that machine into our desired state to run our service, a series of commands that could potentially fail, what we can do is we can take this artifact and we can push it over the wire. And this artifact contains everything that's necessary to bootstrap a host into a known state to run this service. So it's important to note that this process that I'm introducing, it's not foolproof. There are still ways for unintended changes to seep in. Our goal wasn't to eliminate all of these. It was just to reduce the frequency that they occurred to an acceptable threshold. And today, this process accomplishes that for us. To reflect, we've minimized the changes that seep into production by tightly controlling our build process and ensuring that every build is building against a blessed set of tools for the toolchain. Once we have an artifact, that artifact contains the desired state of production. When we bring it up into production, we know that what's running out there is what we asked for. And finally, that artifact, it's able to be verified. So when I deploy a service to production, if I deploy 1,000 copies of the service, I know that all 1,000 of those came up on the machines in the same state, and that the bits that were pulled over the wire onto those machines were correct. I can also guarantee that the image that I'm pushing over the wire is not just the one that I asked for, but it's also the same image that I ran all my unit tests and integration tests against before. And it's the same image that I did my 1% test against earlier in this presentation. So these are a few of the ways that we're de-risking changes in our system. We're using the strangler pattern for our migration. We're isolating the changes that we introduce to our production systems. We're reducing the blast radius of these changes. And we're reducing the opportunity for unintended changes to get introduced to these systems. So what have these patterns unlocked for us? Where are we in our migration? So this is a graph of all of the traffic coming through the front door of Netflix's infrastructure. The red is traffic that's currently being handled by our platform. So it's about 3/4 of all requests we've already successfully migrated. If you're using Netflix today, there's a good chance that you're using this platform. So let's reflect. Netflix is migrating our API to a serverless development experience for our developers. We're pretty happy with the results we've seen so far, and we attribute much of that success to the investments we're making in de-risking the changes that this innovation is introducing to our system. We're de-risking those changes by isolating the changes that get introduced to production. We're reducing the blast radius of those changes to make sure that we don't cause a global outage when we're innovating. And we're minimizing the unintended changes that get shipped along with our artifacts. So the next time that my friends and my family all gather around their televisions, I can be confident that when they sit down and start playing Netflix, the experience that my systems deliver are going to delight them. Thank you.